I'm going to solve a challenging problem which you have seen already in the homework. This is a hard problem because it involves constant velocity, and the equation for constant velocity, as soon as you see constant velocity, you're thinking about this equation, right, where v is a constant velocity. So let me indicate v as constant with a subscript. Excuse me. The next thing we have to look at is a portion where the person has acceleration. And the acceleration is a constant value. They give us one value, so it's constant. It doesn't change. Constant acceleration. Oh gosh, there's not just one equation for constant acceleration. There's 4 equations. So we're probably going to have to choose one, right? The equations you remember are, they look like Vf equals Vi plus A times delta t, but then there's 4 more. And then, in addition to those 2 things, this problem also has us think about average velocity. So as soon as you see average velocity, what are you thinking? You're thinking about the equation v equals delta x over delta t, where v is the average velocity. Right? The average velocity equation is really almost the same as the constant velocity equation. The only difference is what does the v stand for, average or constant velocity. So look at this. These are 3 flashcards. Make these flashcards so that you instantly know when confronted with constant velocity, here's the equation you need to use to solve for anything. And when you're confronted with constant acceleration, you remember, oh yeah, we're looking at the equations with VI, VF, A, those sorts of things. And whenever you see average velocity, oh yeah, you're thinking about this equation. So make flashcards with these things, right? What we'll see is that average velocity is in fact a bit more complicated. Not only is it delta x over delta t, the form we will use, there's really 2 equations we could write. And the second one, which is what we'll use, is delta x total over delta t total. So put that equation on your flashcard as well as delta x over delta t. Put them both down. And make sure you know which equations apply for each of the 3 situations. Okay? That's a great study technique. Okay, so we're going to need all 3. But first, let's read the problem. The person runs for 12 seconds at a constant velocity of 1.4 meters per second. Then from this velocity, from suggests the velocity will change. Oh yeah, from this velocity the person accelerates. Yeah, the velocity changes. And she accelerates at positive 0.28 meters per second squared for 6.1 seconds. What's the person's average velocity over the entire trip? Okay. The first thing I do, I'm asked to find average velocity. There's only one equation that I can use to find average velocity. So I know I will use that equation. I know. It's the only one we know of. And delta x total is something I don't know right now. So let me take this away. I look at this equation here. I say I have to find this. I know the total time. Whoops, I forgot total. I do know the total time right now because the person runs, the person runs for 12 seconds and then immediately runs after that for 6.1 seconds. So the total time is just the sum of the 2, 18.1 seconds. But I really don't know the total displacement yet. Right? I don't know it. Can I calculate the total displacement as a single value? Well, let's think about that. Let's think about that. To answer the question, could I calculate delta x total just as one whole thing? To answer it, I'm going to move these things away just briefly. And we're going to look at a velocity time graph for the woman's trip. She starts at time when you hit the stopwatch and you say go and watch her run. She starts out with a velocity of 1.4 and she keeps that same velocity for 12 seconds. So for the whole 12 seconds she has it, the same 1.4. Then, over the next 6.1 seconds, so after 18.1 seconds after a total time of 18.1 has passed, from 12 to 18.1, she accelerates. The slope of a VT graph is acceleration. Her acceleration is positive, so the slope will have to be positive during this next portion. And her acceleration is constant. It remains at 0.28. So the slope is constant. A positive constant slope looks like this. Like that. Now, you did not have to draw a VT graph, but here's why I've done it. I've done it so that you can see clearly her trip has two segments, A and B is what I'll call them. And whatever displacement she has during A will be different from the displacement she has during B. So let's call the two delta XA and delta XB just so we don't get confused. What were we trying to find? Oh yeah, look at this. We want to know what's the total displacement. We need to calculate that along with total time. Whoa, dropped the tote. We need to know delta X total. We need to know delta T total if we will successfully solve for V average. So now, hopefully what you see is delta X total will simply be the sum of delta XA and delta XB. We have to find her displacement for the first segment, find her displacement for the second segment, and add the two displacements together to answer this question. Okay, so let's get started. Let's find her displacement in segment A, the first segment. Okay, I'm going to move this away just temporarily. First, let me do this. Delta X total, I can rewrite as A plus B, delta XA plus delta XB, over delta TA plus delta TB. Whoa, TB. Yikes. And that's how we're going to solve for V average. But we're not ready to do it yet, because first let's find delta X, the displacement in A. How do we do it? We look at the condition. We look at what's happening physically. In A, we have constant velocity. So we write the equation for constant velocity. It's this. Do we know the value of her constant velocity V? Yes, we do. Her constant velocity V is 1.4. So I'm going to put in positive 1.4 meters per second for V. Right? That's her velocity during B. During section A. Do we know her time during section A? Yes, we do. A lasts for 12 seconds. Do we know her displacement for segment A? Oh no, of course not. We're trying to find the displacement, so let's go ahead and put our A subscript. Right? This in the numerator is the displacement during segment A when she has this velocity for that amount of time. So if you wanted to, you could have added your subscripts a long time ago. You could have said, hey, I'm going to apply this equation for segment A. That means I'm going to add an A to all of these quantities, to the variables. And that's not a bad way to go if you like subscripts. I do. Whoa. I like subscripts, so I like to put those things into the equation. I modify the equation to reflect the way that I've been applying it, or how I'm about to apply it. I'm applying this equation for A, segment A. Okay then, segment A has a displacement equal to 1.4 times 12. What's that? What's 1.4 times 12? Trusty calculator. We ask, tell me 1.4 times 12, and it says 16.8. We just found delta X in segment A. Now we need to find delta X in segment B, and then we can solve. So I'll bring that back in a second. How do we find delta X in B? we look and we see which equations will we have to use. Well, in segment B, the person has a constant acceleration. And we know the value of that acceleration. It's positive 0.28. So as soon as you realize that there is constant acceleration, as soon as you identify what's happening physically, constant acceleration, you say to yourself, we have 4 equations we're going to have to choose from, right? They are these equations. I won't write them all out, but you remember what they are. You have them in your notes. So now we know which equations we'll be choosing from, but let's go ahead and write down the givens so that we can figure out which choice is correct. That's the acceleration. We know this segment B lasts for 6.1 seconds. What else do we know? We know that the person starts with 1.4 meters per second as the velocity. She accelerates from this velocity. And what does she accelerate to? Well, some other end velocity. So clearly for 1.4 is the velocity she has at the beginning. That's what she starts with. She accelerates from that velocity. What do we need to find? We're looking for the displacement during this portion, which we're calling delta xb. So you choose the equation with those 4 things. It's this one, di delta t plus 1/2 a times the time squared. And you know what? Go ahead and call it delta x sub b, since that's the special name we've given to this particular displacement in portion B. So we can calculate. We plug in the values that were given. 1.4, the time is 6.1, the time is 6.1. The acceleration is 0.28, I'm running out of room. The time again here is 6.1. Don't forget to square the time. I'm going to delete all this and move my work over. I'm racing the clock, but more importantly, I'm racing the clock of your attention span, aren't I? Maybe I should make some jokes. I'm reading this really great book right now. It's all about anti-gravity. It's so good, I can't put it down. Yuck, 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 yuck. Uh-oh, my calculator's not working. Let me find a better calculator. So hopefully that just extended the amount of time you'll pay attention to me. Okay, I get 13.75. Delta xb is 13.75 meters. Wonderful news! I've just found the 2 things that I needed. Delta xa and delta xb. Uh-oh. Oh gosh. So what am I going to do? I will now finally finish up the work I started. I'm going to find the average velocity. You plug in delta xa. You replace that with the value you calculated, 16.8. Delta xb will go away. We're going to replace it with the value, which was 13.75. And lastly, we have to plug in delta ta and delta t sub b. Delta t sub a, the time during a, how long did a last? For 12 seconds. Those top numbers had meters as their unit. And 12 seconds was the time of a. The time of b was 6.1. You perform this calculation, and what do you get? You get the answer, and the answer is... Uh-oh, my calculator's dying. Well, you get your answer, and I'm about to run out of time on the video. 16.8 plus 13.75. We want to divide that by 18.1. 1.7 meters per second, unless I did this with too much haste. But what I just got right now, 1.7 meters per second. That's the average velocity. It's positive. And that is our answer. Good work.